Students, we will start the e-learning of our course, Chemistry of Solution. In this course, we will study in Chapter 1, the general introduction, in Chapter 2, the acid-base equilibrium, in Chapter 3, the complexation reaction equilibrium, in Chapter 4, the precipitation and the dissolution equilibrium, and in Chapter 5, the oxidation reduction equilibrium. The objective of this course is to determine the type of donor and acceptor in any chemical reaction. For example, in the case of the acid-base, the acid is donor of H3O plus or H plus, and the base is acceptor of H plus or H2O plus. So the acid is donor and the base is acceptor. And the particle exchanged between the donor and the acceptor in this case is H plus. Then we have to calculate the concentration of the particle exchanged between the donor and the acceptor, then Px equal minus log x. In case of the acid base, the particle exchanged is HCO plus, so we can calculate the concentration of HCO plus in the solution, then pH equal minus log HCO plus in the solution. And we have to calculate not only the concentration of the particle exchanged X, but the concentration of all other species present in the solution. These four objectives will be repeated in all chapters, in Chapter 3, Chapter 4, and the introduction. What is the definition of solvent and solute? Consider, for example, the dissolution of a certain amount of NaCl, which is the table salt, in a cup of water. The water is present in greatest amount, so the water is the solvent. NaCl is present in lower amount, so NaCl is the solute that is dissolved in the solvent, which is water. The solute can be three types. The solute can be liquid, for example, the alcohol solute in water as solvent. Or the solute can be solid, for example, the salt in the seawater. Or the solute can be gas, for example, the oxygen gas, which is dissolved in our blood. The solute can be divided also into two families. We have solute, which is electrolyte, and solute, which is non-electrolyte. Consider the example of dissolution of NaCl in water. NaCl in water will be dissolved and transformed to ions. So this solute is called solute electrolyte because its dissolution forms ions. Consider the example of dissolution of one piece of sugar in a cup of water. The sugar is dissolved in water, but the sugar is dissolved in water and it will keep its molecular form as C6H12O6 and would not form ions. So the solute sugar is a solute non-electrolyte because it does not form ions after dissolution. The electrolyte is also two types. If the dissolution of the electrolyte in solution to ions is complete, for example, consider NaCl in water, 1 mole of NaCl will form 1 mole of Na plus and 1 mole of Cl minus. So the dissolution of NaCl is water is complete and it will dissociate completely to ions. So NaCl is an electrolyte, strong. Consider the example of the weak acid HA. HA in water will dissociate to A minus and HCO plus, and this dissociation proceeds till the equilibrium. So 1 mole of HA would not form 1 mole of A minus or 1 mole of HCO plus, will form less than 1 mole. So the dissociation of HA in water is partial, and HA in this case is called electrolyte weak. The formation of the solution. Consider this figure where we dissolve a solute, NaCl, in a solvent which is water. And when water is the solvent used, the solution is called aqueous solution. The solution is formed by dissolution of the solute in the solvent. And this process of dissolution is divided into two main mechanisms, the dissociation and the solvation. If we consider, for example, the solute NaCl, before adding it to the solvent, you know that Na plus is bound to Cl minus in the crystal because the crystal has a crystal lattice energy studied in the thermodynamics in the first semester. And you know also, according to Vesper, that the shape of H2O is bent and oxygen is more electronegative than hydrogen, so oxygen has a partial charge delta minus and hydrogen has a charge delta plus. When we put the solute in the solvent water, we will have interaction between the molecules of the solvent and the particles of the solute. For example, Cl minus, the negative ion, the anion, will interact with hydrogen of H2O, which is the positive pole, and Na plus, the cation, will interact with the O minus of H2O. So we will have two types of interaction. We will have attraction Cl minus Na plus, and we will have interaction Cl minus solvent and Na plus solvent. If the attraction between Cl minus and Na plus is less than the interaction between the ions and water, so in this case, Na plus will dissociate from Cl minus and we will have dissolution of NaCl. Or if the attraction X minus Y plus is greater than the interaction minus solute water plus solute water, in this case, the minus ion, the anion, will be bound to the cation, and we will not have a complete dissociation. We will have, for example, a partial dissociation. For example, AgCl is partially soluble in water. After the dissociation of Na plus and Cl minus in the solution, these ions will be surrounded by water molecules, and this process is called solvation or hydration. Of saturations of solutions. Suppose we want to dissolve 100 grams of NaCl in a certain volume of water, which is the solvent. We observed at the beginning that 5 grams of NaCl are soluble, and we have 95 grams that are still dissolving. So this solution is called unsaturated because we can dissolve more solute in this volume of solvent. At the dynamic equilibrium, we observe that 91 grams of NaCl are soluble, and we have 9 grams that are precipitated. That means in this volume of water, we can dissolve maximum 91 grams of NaCl. So the solution is saturated by the solute. We heat the solution till 50 degrees, and we observe that this 9 grams precipitated are dissolved in the solution, and we have practically 100 grams of NaCl that is completely dissolved. We cool down the solution from 50 degrees till 25 degrees, and we observe that we have 100 grams of NaCl that is dissolved in the volume of the solvent. In this figure, we can dissolve only 91 grams at 25. But here, at this temperature 25, we dissolved more than the maximum amount. We dissolve 100 grams due to the increase of the temperature. So this solution is super saturated. If we cool this solution, or we keep the solution at 25 for a while, we observe that 91 grams of NaCl are dissolved, and we have appearance of 9 grams of precipitate. So we return to the dynamic equilibrium, to the saturated solution. A saturated solution, by definition, is a solution containing the maximum amount of the solute which can be dissolved at equilibrium. The unsaturated solution is a solution that can dissolve more and more solute, and the supersaturated solution has more dissolved solute than its capacity, so has more dissolved solute than the saturated solution. Definition of the term solution. Solution is a term to describe a homogeneous mixture where we have only one phase. For example, if we consider the atmosphere, we have several gases that form one layer. So we have solution of gas. If you have a mixture of copper and iron, and you could not distinguish between copper and iron, so you have a solution of solid. But in general, the term solution is used to describe liquids. The composition of the solution can be different if the amount of the substance dissolved is changed. The substances are all in the gas state, so we have solution of gas, or the substances are all at the liquid state, we have a solution of liquid, or we have, for example, several states, aqueous, liquid, and gas, but they form one layer, so we have a solution. The heterogeneous system, in the heterogeneous system, we have more than one layer. For example, CaO solid plus CO2 gas that gives CaCO3 solid. We can distinguish between the two layers between the solid and the gas, so this system is heterogeneous. Or if you have ice that melt to liquid, you can distinguish between the ice and the liquid. You have two layers, so this system is heterogeneous. A solution is electrically neutral. That means the quantity or the equivalent of the positive charge is equal to the quantity or the equivalent of the negative charge. And the electroneutrality principle is given according to the formula: the sum of ZiCi equals 0, where Zi is the charge of the ion I, and Ci is the concentration of this ion. Let us consider the solution containing Na plus and SO4 ions. SO4 is double charge minus, so its equivalence is 2 times its concentration, where Na is monocharged, so its equivalence is 1 times its concentration. When Na2SO4 is dissolved in water, we obtain, according to this total reaction, Na plus and SO4 ions. So what are the ions present in this solution? First of all, we have the positive ion Na plus and the negative ion SO4 that result from the direct dissociation of Na2SO4. And we have also HCO plus and OH present in the solution from the autoionization of water. As we said, each monocharged ion is equivalent to a quantity of charge 1 time its concentration, and each dicharged ion is equivalent to a quantity of charge 2 times its concentration. So if we apply the principle of electroneutrality on the solution of Na2SO4 in water, we will obtain this equation. Na plus has a charge 1, so 1 times its concentration, plus H2O plus has also a charge plus 1 multiplied by the concentration of HCO plus, and this are the positive ions, equal SO4 has a charge 2 so 2 times concentration of SO4 plus 1 times concentration of OH minus. Take a reaction from reactants to products. We have conservation of matter, and we have conservation with respect to the number of atoms. That means the number and the types of atoms present in the reactants are equal to the atoms produced in the products. We have conservation of the electrical charge. The charge of the reactants is equal to the charge of the product. And we have also the conservation of mass, where the total mass of the reactant disappeared is equal to the total mass of the products formed. The following relation applies to any substance I. The number of mole reacted is equal to the number of mole initial minus the number of mole remained. So an initial equal N remained plus N reacted. And since we are working in solution, and in general the total volume of the solution is constant, so we divide the N initial by V total, the N remained by V total, and the N reacted by V total, and we obtain C initial equal the concentration remained plus the concentration reacted. Consider this example of a puzzle formed of 4 pieces. If we separate the puzzle to 4 forms, the initial puzzle is equal to form 1 plus form 2 plus form 3 plus form 4. So the initial puzzle is the same as piece 1 plus piece 2 plus piece 3 plus piece 4. So the initial concentration of the puzzle is equal to the concentration of piece 1 plus concentration of piece 2 plus concentration of piece 3 plus concentration of piece 4. So if you have a substance initially that is transformed to several forms, the initial concentration of this substance is equal to the concentration of any form of it. The solution is characterized by the molar concentration or molarity, noted Cm or simply capital M. The molar concentration is equal to the number of mole of solute in mole divided by the volume of the solution in liter. So the unit is mole per liter or simply molar capital M. A direct application: calculate the molarity or the molar concentration of a solution if 2 grams of NaCl were dissolved in 250 milliliters water. The molar concentration is equal to the number of mole of solute divided by the volume of the solution, and the number of mole of solute is equal to the mass of the solute, which is 2 grams, divided by the molar mass of NaCl equal 58.5, divided by the volume of the solution in liter, which is equal 0.25 milliliter, equal 0.137 mole per liter or molar. To note that the volume of the solution is equal to the volume of the water plus the volume due to the addition of 2 grams of NaCl. But we suppose that the addition of 2 grams of NaCl did not change the total volume, so in this case the total volume is equal 250 ml. Another example: how much NaOH would you need to make 500 milliliters of a solution NaOH of concentration 0.70 molar? The molar concentration is equal to the number of mole of solute divided by the volume of the solution. So the number of mole of the solute is equal Cm times V. Cm equals 0.7 times the volume of the solution, which is 0.5 liter, and in this case also we suppose that the addition of NaOH did not change the total volume, so the total volume is equal to 0.5 liter. So the molar concentration, the number of moles, is equal 0.35 mole, and the number of mole is equal to the mass divided by the molar mass. So the mass equal N times the molar mass equals 0.35 times the molar mass of NaOH, which is equal to 40. So the mass is 14 grams. What is the meaning of a solution 0.137 mole per liter? That means in 1 liter of the solution we have 0.137 mole of the solute NaCl. The solution also can be expressed by the mass concentration C small m and the mass concentration is equal to the mass of the solute divided by the volume of the solution. The mass of the solute in gram and the volume of the solution in liter, so the unit of the mass concentration is in a gram per liter. We have relation between the mass concentration and the molar concentration of a solution. The molar concentration equal the number of mole of solute divided by the volume of the solution. The number of mole of solute equal the mass divided by the molar mass times 1 over V. The mass divided by V is equal to the mass of the concentration divided by the molar mass of the solute. So the mass concentration of a solution is equal to the molar concentration of this solution times the molar mass of the solute dissolved in this solution. Solution can be expressed by its molality, and pay attention that the molality MOLA is different from the molarity MOLAR. The molality, by definition, is equal IN divided by M. I is the number of particles of solute after dissolution. For example, NaCl dissolved in water will give Na plus and Cl minus, so it will give 2 particles, Na plus and Cl minus, so I equal 2 in this case. N is the number of moles of the solute in mole, and M is the mass of solvent in kilogram. Pay attention also that the molar concentration is equal number of mole over the volume of the solution, but the molality is equal to the number of mole of solute divided by the mass of the solvent in kilogram. So the unit of the molality is mole per kilogram, or simply small m, that means molal. An application: what is the molality of all ions in a solution made by addition 1 gram of CaCl2 to 50 ml water? First of all, CaCl2 dissolve in water according to a complete reaction to give Ca2 plus and 2Cl minus. So the dissolution of CaCl2 gives in total 3 particles, 1 Ca2 plus and 2 Cl minus, so I equal, in this case, I equal 3. The number of moles of the solute CaCl2 is equal to the mass divided by the molar mass is equal to 1 divided by the molar mass of CaCl2 equal 112, so equal 0.00895 mole. The molality of the solution obtained is equal to I, which is the number of particles equal 3, times N, 0.00895, this is the number of mole of the solute, divided by the mass of the solvent. And in this example, we have 50 ml, we have a volume. But since the density of water is equal to 1, so 50 ml is equal to 50 grams. And in this case, the mass of water in kilogram equal 50 times 10 to the minus 3 in kilogram. So the molality is equal 0.537 molal, or 0.537 mole per kilogram. Action of A in a solution is equal, by definition, the number of mole of A divided by the total number of moles, and the mole fraction is unitless. Suppose you mix A plus B plus C. So XA equal NA divided by N total, XB equal NB divided by N total, and XC equal NC divided by N total, and N total equal NA plus NB plus NC. So if you add XA plus XB plus XC, you will obtain NA plus NB plus NC divided by N total, and NA plus NB plus NC is equal to N total. So XA plus XB plus XC is equal to N total divided by N total is equal to 1. So the sum of the mole fractions of all species present in a solution is equal to 1. The mass percent, by definition, is equal to the mass of the solute divided by the mass of the solution times 100. And pay attention that the mass of the solution is equal to the mass of the solvent plus the mass of the solute. A direct application: calculate the mass percent of sodium chloride if 5 grams of table salt of sodium chloride is mixed in 1 liter of water. The percent P, by definition, is equal to the mass of the solute, and the mass of the solute is equal to 5 grams divided by the mass of the solution. The mass of the solution is equal to the mass of the solute plus the mass of the solvent, and the mass of the solvent in this case is equal to 100 grams, since the density of water is equal to 1. So percent P equal 5 divided by the mass of the solution, 1000 plus 5 times 100 equal 0.5%. We can express also the solution according to its normality, and by definition the normality is equal to the number of equivalent gram divided by the volume of the solution. N equivalent is the number of equivalent grams, and V is the volume of the solution. In case of acid, if you have acid in a solution and you are searching the normality of the solution, the number of equivalent is the number of mole of HCO+. And if you have a base in this solution, the number of equivalent is the number of mole of OH-. In case of the redox reactions, the number of equivalent for oxidant is the number of electron gained, and the number of equivalent for reductant is the number of electron lost.